right, this video is going to be for calculus, infinite series unit, and we're talking about absolute versus conditional convergence, which is something that we have to be considering whenever we have series that have mixtures of positive and negative terms. All right, we're going to define this, and then I'll learn methods for dealing with that. So sometimes you have a series that has both positive and negative terms. Now that might be an official alternating series, which means every other term alternates in sign, like plus minus, and so on, right? With that -1 to the n structure and -1 to the n minus 1. But you could have other forms that generate terms which are mixtures of positives and negatives, like this series, n equals 1 to infinity of sine of n over n squared. N squared in the denominator is always positive. But sine, if you take the sine of 1, the sine of 2, the sine of 3, the sine of 4, some of those signs are positive and some are negative. In fact, if you write out the first terms here, you end up getting that the first couple of terms are positive, and then the first three terms, and then there's a few negative terms. So it seems like about every third term or so it changes. Right. So what do we do when we have mixtures of positives and negatives? Well, it turns out one of the things that we can use to learn about the convergence of such a series is to investigate a series of the same form but with absolute value. In other words, just temporarily throw away the negatives and determine what happens, right? So let's say that we did that. Let's say that we took the absolute value of this generating rule. So this is like the AN rule, and this is a series of the absolute value of AN. Okay, so if we did that, we could use a direct comparison test to the series 1 over n squared, because 1 over n squared is a p series with p2, so that converges. And if you look at the rules here, right, the absolute value of sine of 1 over n squared is always less than or equal to 1 over n squared, because sine is always less than or equal to 1. Right? And since this side is converging and this side is underneath it, it's going to also be squeezed down and converge as well. So although it's harder to see what the negatives in the way, throwing away the negatives, we could use this absolute value and do a direct comparison test. The question is, how does that help us in evaluating the convergence of the original series with the positives and negatives? So we actually need another theorem. And there is a theorem. It says this: if a series where the terms have been made all positive converges, then the series with the negative terms in also converges, right? So if we evaluate the absolute value series and find that convergence, automatically the series with negatives also converges by this theorem. All right. The formal proof of this is in a textbook if you want to see that, but you can kind of see why this would be true, right? It doesn't really matter if these terms are negative or positive, but imagine this, okay? If these were forced temporarily to be positive, so we made these positive, then if we were adding up numbers here, so we added up a 0.84 and a 0.22 to that and a 0.15, in other words, these heights are these numbers here. If I turn these around and make them positives, so this is a positive number and a positive number and a positive number, and when I add all those positive numbers up, I get something that's approaching a number and not going to infinity. Then if I allow some negatives in there, if anything, that's going to reduce that number a little bit and make it converge even stronger, right? So, if all the terms being positive adds up to a number, adding negatives in is going to even converge faster to that number. That's, to me, the intuition of why this works. All right. So the converse of that, though, is not true. If you say the converse would be, if a series converges, then the absolute value of the series has to also converge. But that's actually not true. Let's consider this series here. Let's say we have this truly alternating series with every other term positive and negative here. Its terms are 1, negative 1/2, positive 1/3, negative 1/3. If we do the alternating series test on that, the limit as n approaches infinity is 0. So that's the first criteria. And we can show that 1 over n plus 1 is always less than 1 over n. So this one is decreasing, and therefore that means that the series with the negatives in here converge, right? So if I allow the positives and the negatives to cancel each other out, they do converge. The sum gets small fast enough or smaller, or grows less quickly so that it converges to a number. But if we did take the absolute value here and threw this part away, That series, 1 over n, is a p-series with p of 1 which diverges. So, just because you have a series where the positives and the negatives are mixing to converge, if you force the negatives to be positive terms, that does not necessarily always converge. All right. So these ideas are encapsulated in these two statements here. So a series is called absolutely convergent if it converges even with an absolute value. So even if you're not allowing the negative terms to cancel some of the positive terms out somewhat, right? So if the absolute value of a series converges, then you can state that the series without the absolute value definitely also converges, and we call that situation absolutely convergent. But if you have a series where the original series with positives and negatives mixed in converges, but taking the absolute value that forces the negatives to become positive diverges, then we say the series conditionally convergent. It requires its negatives to do some cancellation in order to converge. All right, so two new terms, absolutely convergent and conditionally convergent. These apply only to series that have mixtures of positive and negative terms. All right, so you can turn this into kind of a procedure. This is personally the way I think of it. If you have a series and it has some mix of positive and negative terms, then first check the convergence of the absolute value of the series. Just throw away the parts that are making it a negative or force it to be positive terms. If that converges, then you stop and say this converges absolutely, because it converges in all cases. Okay, if that does not converge and it diverges, then go ahead and do a second step and perform an alternating series test. If that converges with the negatives allowed to mix, then it converges conditionally. Okay, if that one diverges, then technically you're not using the alternating series test to show that it diverges, but then it usually will diverge by another test, like the nth term test, and you can declare that the whole series diverges. So when you have series with mixtures of positive and negative terms, they could either converge absolutely, converge conditionally, or diverge. All right, so we'll take a look at some of each of those examples here in the next examples here. Let's say we want to determine whether the series converges absolutely, conditionally, or diverges. And at least for Mr. Cook and I, for our tests, we only intend for you to do this procedure when the problem states that it's asking you to separate absolute versus conditionally convergent. If the problem just says, does the series converge, and it's an alternating series, you can just do the alternating series test as we did in a previous lesson and be done. But if the problem asks you about absolute versus conditional convergence, then you have to do this procedure. All right, so what I'm going to do is first, I'm going to check, I like to write this, I'm going to check the series n equals 1 of the absolute value of an. Okay? Now what that would be the series n equals 1 to infinity. I'm just going to throw away this part here that's making it change signs, 1 over n squared. And that is a p-series with p equals 2, so that converges. Right, that one converges. Right, and then since that converges, I don't need to do anything else. If throwing away the negatives converge, then that means that the series will also converge if the negatives are in there. So I would then finish this by saying since. Now I would probably be specific if I was on the AP test. I would say since 1 over n squared converges by the p-series test, the series n equals 1 to infinity of negative 1 to the n plus 1 over 1n squared converges absolutely. So the final conclusion is that the original series converges absolutely because throwing away the negatives and just using absolute value converges. So there's a case of this first thing on the tree. That's this one, going down this path and finding we stop there when it converges. Okay. Okay, let's look at another example. Got an alternating series here, so there's a mixture of positive and negative terms. First thing we'll do is check the absolute value of this, right? So that is just going to be sum from n equals 1 of 1 over n plus 3. Okay, so for this one, maybe we could do a comparison test. And I think let's do a limit comparison test. So let's do a limit comparison. Compare to the simpler form, n equals 1 to infinity of 1 over n. So 1 over n, that is going to be a p-series with p equals 1, so that diverges. And then we can continue this and say, all right, for limit comparison, we have to take the limit as n approaches infinity of the two rules. So we'll use the original rule and the simpler series rule, which is the limit as n approaches infinity of n over n plus 3, which is 1. So since that's finite and positive, that means that these series are linked. So I would say since the limit as n approaches infinity of 1 over n plus 3 over 1 over n is 1, which is finite and positive, and the series n equals 1 to infinity of 1 over n diverges by the p-series test. The original absolute value version, which is 1 over n plus 3, also diverges by the limit comparison test. Okay, and that is the absolute value. So at this stage, we tried to check for convergence, but found that the absolute value diverges. So we're here. And that means the next thing we're going to do is perform an alternating series test. Okay, so now we're going to do an alternating series test by allowing the negatives to come back in. So now we'll do an alternating series test on the original series, n equals 1 to infinity of negative 1 to the n plus 1, 1 over n plus 3. So first we check the limit as n approaches infinity of the generating rule ignoring the sign, and that is 0, so that's good. And then secondly, I need to show that an plus 1 is less than or equal to an. We have 1 over, if I add 1 to this, that's n plus 4, is less than or equal to 1 over n plus 3. That's true. So therefore, well, let me just jump straight to it in the conclusion. Therefore, this converges by the alternating series test. And that means that since we had something, let me go back to the tree, that diverged when we threw away the negatives, but converged when we allow the negatives in, this is conditionally convergent. So I think the clearest way to write this up is like this. You can say, since n equals 1 to infinity of the absolute value of negative 1 to the n plus 1, 1 over n plus 3, diverges by limit comparison, and the series n equals 1 to infinity of negative 1 over n plus 1 without taking the absolute value converges by alternating series test. You can say, therefore, the series n equals 1 to infinity negative 1 to the n plus 1, 1 over n plus 3 converges conditionally. Right? You have to have the negatives do some canceling for it to converge, so it converges under that condition. All right, so that's how I would show the work for that example. Okay, let's take a look at another example. I don't think we have too many more. Yeah, this is the last of the examples, and then just another little point to finish things off. All right, same thing. We're going to determine whether or not the series converges absolutely or conditionally. So let's start with an absolute value. We'll check the series of the absolute value, which would be 1 to infinity, ignoring this part, 2n plus 3 over n plus 10. That's hard to read. N equals 1 to infinity 2n plus 3 over n plus 10. All right. So for this one, let's see. Maybe we could just do the nth term test. Looks to me like if we just take the limit as n approaches infinity of the generating rule, that is equal to 2, which is not 0. So therefore, this diverges by the nth term test. Okay, so if it already diverges before we even start, the absolute value diverges, then it's not going to converge. Well, no, wait, I guess we still need to check. Sorry, we're here on the tree. Let's take a look. So here, we've tried this diverges, so we're currently here. Now we're going to perform the alternating series test. Okay, so let's do the alternating series test. So the alternating series test, we will take the limit as n approaches infinity. To be specific, I'm doing this on the alternating series. -1 to the n plus 1, 2n plus 3 over n plus 10. So we take the limit as n approaches infinity of the generating rule without the sign in there, and that's 2, which is not 0, so it fails the alternating series test, which means that we have to come up with some other test, but we can say that based on that work over there, because the nth term test does not require that we account for the sign, we can say that this diverges by the nth term test. Okay, so let's be specific. So we're going to say, based on this work, the series n equals 1 to infinity -1 to the n plus 1, 2n plus 3 over n plus 10 diverges. There's no diverging absolutely. We just say diverges, and it's because of the nth term test. Okay, so there's the three cases. We can have something that converges or that converges with the absolute value, in which case it converges absolutely. We don't have to check with the signs mixed in. We can have something that diverges when we do the absolute value and throw away the negatives, but converges when we do the alternating series test. So we say it converges conditionally, or we can have something that diverges in both cases by the nth term test. Right. So why is this important? Well, I mean, we definitely will be asked questions like this on our test and could be on the AP exam. There's another interesting thing that's not intuitive, but kind of, I think, interesting, counterintuitive. It turns out if you rearrange the terms in an infinite series, you still have an infinite number of terms, but this is not intuitive. It can change the sum to which a series converges to if you simply rearrange the terms. Okay, so this is not an issue with finite series. If you have finite series, like you have the series 1 plus 3 minus 2 plus 5 minus 4, and you add those values up, the sum is 3. It does not matter how we rearrange the terms. But consider this series. We have an alternating series from 1 to an infinite number of terms, -1 to the n plus 1, 1 over n is the generating rule. So that gives me 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5, and so on. Okay, now if you take these terms as is and you try to figure out the partial sum, come up with some sort of expression for the partial sum, we could add 1, maybe, let's see what we got here. Partial sum's adding 1, then 2, then 3, then 4. So if I take this as is, and I take the first partial sum, we would get 1. If I add the next two together, 1 minus a half gives me a half. If I add on a third term, which is 1/3, I go up to 8.83. If I add on another term, and I get minus 1/4. So what's happening is this is starting at 1, and the sum is oscillating around a value. The value that this seems to be approaching, if you look at this, is the natural log of 2. Right, so this is approaching the value natural log of 2, and it suggests that if I were to add an infinite number of these terms, I would get the natural log of 2 as the sum. This series converges to the natural log of 2. Apparently, though, but let's say we did this. Since we have mixtures of positive and negative terms, if you happen to choose to rearrange it this way, where you took the first two terms and added them, and reconsidered that to be a term. So that's now a series. That's a first term. And then I'm going to take this next term, like go up 2 terms and leave that term separate. And then I'm going to take this, so I'm taking these 2 terms together, right? Then I'm going to take this term with this term, so the 1/3 and the 1/6 term. And then I'm going to take the 1/5 term with the 1/10 term. And I'm going to take the 1/7 term with the 1/14 term and squeeze these other ones in. So if I rearrange it like that, 1/1 minus 1/2 minus 1/4, and then plus 1/3 minus 1/6 minus 1/8, and so on. And you come up with a generating rule for this and take the partial sums. So this first term would be 0.5. When I added this in, I get to 1/4. Add the next term, you get to that. These numbers do not approach natural log of 2. They approach a half of that number. So it seems like this is coalescing down, oscillating around a different term. How weird. Just regrouping the terms and redefining a new series on that generates a different sum for that series, even though they're theoretically built from the same series. How weird is that? This only happens with infinite series, and it only happens when you have mixtures of positives and negative terms. So why is this important, and why are we mentioning it in this series? Because there's a theorem that says that if you have a series that's absolutely convergent with positive and negative terms, then the terms can be rearranged in any order, and it will not change the sum of the series. But if you have a series that can be shown to be conditionally convergent, then rearranging the terms will change the sum of the series. All I can say is, once infinity is involved, a lot of things about our intuition don't really work properly. All right, so that's it for this lesson. There's a lot more examples in the homework.